Yeah. Open it, searching Microsoft Edge. Yes. Fine. Screen share. Yeah. So is my screen visible?
Yes, sir.
Okay, okay. I'll make it full screen whenever it is required. Okay. Fine. So good morning to all of you. And the topic which I've chosen for this session is advances in image segmentation. So I think since last couple of days, you have been learning several concepts of deep learning and computer vision, of course, and generative models as well. So we'll see the applications of those models, especially convolutional neural network and transformers, then to the foundation models, right, in the field of, especially in the field of image segmentation. Here's the outline of my session. I'll start with, of course, discussing what exactly image segmentation is and how it is different from different tasks like classification, which, I mean, some of the concepts looks very similar, but we'll try to see it in detail, that how segmentation is different and how segmentation and why segmentation, first of all. Then we will see why we're interested in solving these kind of problems with the help of deep neural networks, right? Why not traditional approaches? Although we know traditional approaches do not require the labels, especially the ground truth, because most of them are unsupervised in nature. But still, we are planning to solve the problem with the help of convolutional neural network or transformers or some foundation models. What is the reason behind it? Then I'll take you through the journey from CNN to the foundation model, how this field has been progressed over the years, starting from 2014 till date, right? I mean, basically, I will discuss about the evolution of these architectures, image segmentation or deep learning architectures that are specifically designed for solving image segmentation tasks. So in that, I will talk about some of the CNN-based architectures, very popular till date, and some of the vision transformer-based architectures. And of course, at the end, I will talk about some of the foundation models for segmentation. And one of the most powerful, successful foundation model known as segment anything model, right, that I will discuss. And I'll show you some of the case studies, I mean, some of the works which we have done since last 3-4 years. One is, I mean, both of them are in the field of medical imaging. I mean, medical image segmentation. I'll also tell you what is the need of segmentation in medical imaging. And if you go through the literature, you will also find that most of the popular image segmentation algorithms are initially validated on medical image datasets and later been adapted to other computer vision tasks related to segmentation. And of course, we'll also talk about some of the challenges what we face while solving or while adapting the models like foundation models for solving a variety of segmentation tasks. Now let us start with what exactly image segmentation is. So when we talk about image segmentation, it is nothing but simply partitioning the images into multiple segments or objects that are associated with a particular class. This set of examples you can see, our goal is to simply partition the image into different objects of our interest then that are associated with some classes. You can see some of the examples over here. Look at the first example, which is there in the top left-hand corner. Our goal is to segment this particular image into two categories, into two objects. One is the person and one is the bike, right? So this is, I mean, if you want to, and here, how it is different from the detection problem. In detection, you are interested in providing a bounding box. But here we are interested in providing clear boundaries of that particular object, which plays a very, very important role in many applications, such as medical imaging, where sometimes the tumor boundaries are very, very important for the clinicians to remove it. Similarly, in case of autonomous vehicle, pedestrian detection is also a very, very important task. In video surveillance, most of the time we need these kind of solutions using image segmentation tasks. Scene understanding problem also we need this kind of task. This is just an example. I'll explain in detail what are the different types of segmentation tasks we have and how it is also different from its close concepts like object detection, classification with localization. I'll discuss in the next slide. Now let's try to differentiate between the very popular task in computer vision, classification, object detection, and image segmentation. So when we say classification, we only use to assign a label with respect to an image, and it is a classification at the image level. So given an image, your goal is to just associate a output level with that particular image. And it tells that what is in the image, basically. And that is what is classification. And what is this classification with localization? So classification with localization will tell what is in the image. At the same time, it will tell where is that object, where is that classified object especially. And you can see one example over here. You can find out the difference between the classification and classification with localization. Here you see. So classification, your goal is just to assign a level which is cat with respect to this image. But in classification with localization, in addition to providing a level, you need to also provide that particular region where exactly that object is residing within the image. So in object detection, you need to identify all possible objects that are present in the image, and you need to also provide a bounding box, right? Of course, you have said, where is that object present in the image? At the same time, you will also provide different labels with respect to different objects. You can see here, there's a dog. Dog is an object. Here is another dog. Here is a cat, right? So there are three different objects over here. One is dog 1, dog 2, right? There are two different dogs, and there's a cat here. That is object detection. We are providing the bounding box as well as the labels. And what it basically tells us, what are the all objects? That's the label, and where are they? That's the position of the bounding box. But in semantic segmentation, when I'm saying actually semantic segmentation, I will also explain, because segmentation is of especially three types. One is semantic segmentation, one is instance segmentation, and another one is panoptic segmentation. But now I'm just considering one that is this one. That's a semantic segmentation. I'll explain in the next slide what exactly semantic segmentation is and what we are trying to do here. So just look at the output. Just look at the output of a semantic segmentation approach here. What it gives us, it basically tells us the classification at the pixel level. Simple classification is nothing but classification at the image level with provide a particular class. But semantic segmentation is such a segmentation which is nothing but known as pixel level classification problem, which finally results in something called as a clear boundaries of the object. Now you see, in case of object detection, it only gives us the bounding box. But now what you are getting is the clear boundaries of that gap, which is very, very useful in some of the applications. Explain in detail what exactly semantic segmentation is and how it is different from instance segmentation, and how instance segmentation is different from actually semantic segmentation. I'll explain in another slide. But here, what type of object is each pixel on the screen? That means you need to identify that pixel either may belong to grass category or cat category or tree category or sky category. It is just a pixel level classification problem. So that means you need to highlight all the pixels of the cat as cat, and which is now represented in yellow color, you can see. And this here you can find out the clear boundaries. That's the difference. And that is why it is very, very important in medical imaging applications, where our goal is to identify where is the tumor, and rest others can be considered as a background. Right? And sometimes you may also find more than one tumors. We'll discuss in detail. Now let us try to define what exactly is the semantic segmentation task. Semantic segmentation means it is a task of grouping similar type of pixels within an image. So how do we formulate this kind of task? With the help of deep neural networks, we cast this problem as a pixel level classification task, as I discussed. So then what will be given to us? Because it's a classification problem, you know that CNNs are very popular for solving classification tasks. And there were also, I think, sessions on CNN that you can design a convolutional neural network models to solve a classification task. But that classification which we have seen is something very different from this classification task. In that classification, you will be given a set of images, right? And your goal is to just provide a corresponding probability values, or you can say just assign a label with respect to each of the images, right? That's simple image classification task. But what I'm saying that semantic segmentation is nothing but as a pixel level classification task. Every pixel, where every pixel in the image will be classified into certain categories. Look at this example here. Here is the input image which is given to us, and now I want to segment this image to multiple objects. And what are the objects in this image? One is sun, one is bicycle, and rest others are background for us. So then what is our task here? My task is very simple, is to just process all these pixels and assign a particular level with respect to this image. Let's say the first pixel here belongs to the person category. The second pixel again belongs to the person category. Maybe the 10th or 11th pixels that belong to the background category. I hope it is clear. It is simply a pixel level classification task. And then we will see how we can use a convolutional neural network to solve this task. Because the traditional convolutional neural network which you have seen cannot directly be adapted to solve this problem. Why? Because it usually generates some probability values. But in semantic segmentation, right, that's the image level classification task. Image is the input, output is just a set of probability values. But here, in case of segmentation, input is an image, output is also an image. And this is sometimes known as masked image or ground truth image. This is the ground truth image, right? And here is the input X, and here is the output Y. Now, X and Y both are in the form of images. Earlier, Y was not an image, X is an image. And Y was just a simple label. But now, X is an image, Y is also an image. So that means the traditional convolutional neural network like ResNet, AlexNet, the popular CNN architectures which you have seen, right? DenseNet, maybe MobileNet and all, could be directly used to solve this problem. So why the name is so-called semantic segmentation? Because we are assigning a semantic category to each of the pixels in the input image, right? You see, we are assigning a level or semantic category with respect to each of the pixels, and that is why the name is so-called semantic segmentation. However, the annotation of this kind of, or getting this kind of ground truth is very, very difficult. And that is why it is written that it is quite annotation intensive. Why it is quite annotation intensive? Because we need pixel level annotations. It is not image level classification where looking at a particular image, somebody can label it. So that means labeling or annotating at the image level is very easy, but pixel level annotation is very difficult. Sometimes this particular annotation may require even 15 to 20 minutes, right, per image. So just think about medical images and all. As we all know that clinicians are always busy, so they have to sit for half an hour, let's say, to just provide a single ground truth image, or they have to annotate, or they have to spend, let's say, 2 minutes to just annotate a single image. So getting this ground truth image is very, very difficult in case of semantic segmentation. So once you will get a set of X or set of input images in the set of Y, set of X and set of corresponding ground truth images, then only you can think of finding out the relationship between X and Y. Of course, that is the job of this, the learning algorithm, to find out the relationship between X and Y. But you must have a set of inputs as well as a set of outputs. And outputs in the form of the ground truth mask. And that is why it is very, very difficult. But then why we're interested in this? Because then the traditional algorithms. And what are the traditional algorithms we have? I'll come back to this slide again. Right. So these are the traditional algorithms you might have heard about. It all starts from a very simple technique known as thresholding, through which we usually perform segmentation, but we know it is a purely manual approach. So there are other approaches like watershed, graph code, region growing, and the very popular k-means clustering, which is an unsupervised approach, right? Through which you can cluster the similar type of pixels, which is also known as image segmentation, because your group is to because your task is to group similar type of pixels that are present in the image, right? But these are again unsupervised. These algorithms do not require any ground truth, and these are of course unsupervised approaches, but not that accurate or cannot match the real-time performance. So that is why we are interested in learning the segmentation approaches, where although we need although we need a pair of X and Y images, but still we're interested in this. Of course, so there are other approaches, other paradigms, learning paradigms through which you can remove the problem of the data scarcity in this case, or you can remove the problem of annotations just by introducing something called a semi-supervised neural. We'll discuss later on. If some of the images are annotated and many images are not annotated, then what you will do in that case, right? So even pixel level annotations are sometimes not required. Just using some of the informations, some partial informations, you can also solve the segmentation task. That is sometimes known as is known as semi-supervised segmentation approaches, and some of the approaches are based on weakly supervised segmentation approaches, which I will discuss at the end of the session, right? So now let us try to define what are the different types of segmentation. I will only focus on semantic segmentation. If time will permit, I will also discuss how to actually, I'll just give you the idea that how to solve this instance segmentation task. So for solving actually this instance segmentation task, we should have also knowledge on object detection and all, right? I hope you have already studied object detection, like, the very popular algorithms like faster RCNN, fast RCNN, and YOLO kind of algorithms are also required here to solve instance segmentation. But before that, let us first discuss the semantic segmentation is different from instance segmentation and panoptic segmentation. The three forms of segmentation actually. One is semantic, one is instance, and one is panoptic segmentation. Now let us look at the same example and try to identify the differences here. Look at here. Semantic segmentation. What is our goal? Just assign a semantic category, right, to each of the pixels. Doesn't matter. So that means all persons are classified as person, all vehicles are classified as vehicles over here. But in case of instance segmentation only care about the objects, right? And it differentiates between the different objects of the same class. Let's say there are two persons, right? So it will say it is person number 1, it is person number 2, it is vehicle number 1, it is vehicle number 2. But semantic segmentation doesn't care about this. It simply classifies that all are, whether all are vehicles, all are persons, all are trees, roads, like that. But instance segmentation is mostly focused on the objects part, right? It tries to find out the difference between objects. Like in case of object detection, also you have seen that you can easily identify different objects, right? Or you can detect different objects along with their levels. But here we are providing the boundaries as well, right? And you are only caring about the instances or the objects that are present in this image. So what about then panoptic segmentation? So panoptic segmentation is just the union of semantic segmentation and instance segmentation, and is the most challenging one compared to semantic as well as instance segmentation. That's the current trend of segmentation known as panoptic segmentation. Okay, so we'll start focusing on semantic segmentation, and then I will show you, or I will basically discuss, or I'll give you a hint that how to solve this instance segmentation. Solve instance segmentation. If you know how to solve semantic segmentation, as I said, it is just a union or combination of both instant and semantic segmentation. You can just combine the output of two networks. One network will be dedicatedly designed for instance segmentation. I will explain. And there will be one network which will be dedicatedly designed for semantic segmentation. You will just combine the output of those two networks. You can solve the panoptic segmentation. That's the simplest way to do how to solve panoptic segmentation. But there are also other ways to do or to solve panoptic segmentation. Now let us talk about the evolution of this segmentation approaches, of course, because our goal is to solve the segmentation problems with the help of course, convolutional neural network, because you have seen the power of the convolutional neural network, right, in learning the hierarchical features and ultimately giving better performance, or you can say state-of-the-art classification performance in comparison traditional machine learning algorithms. So then people thought of how to basically use this convolutional neural network to solve segmentation task. So what they observed that, as I said, directly you cannot use resonate kind of architecture to solve the segmentation task because it does give output as an image. It usually gives a set of probability values, right? And based on the maximum probability value, we usually solve the problem. That is what we do, right? In case of any segmentation, any classification task. So you'll be given like a set of images. Let's say these are set of images which are given to us, and multiple convolutional layers, ReLU layers, or maybe some variants of the ReLU layers, and then probably set of layers, right? Then pooling layers and all, right? And finally, you'll be having some set of fully connected layers, and then you'll get a set of probability values here, probability 1, probability 2, let's say probability C, a C of classes, because you are using, let's say, softmax activation function, right? So softmax activation function. So then based on a set of probability values, right? And then we know how to train the model, right? So then we usually represent the outputs in one-hot encoding. Outputs in one-hot encoding process. Let's say there are C number of classes. Let's say C is nothing but 5 here. C is equal to 5. So you'll get 5 different probability values. Say I know that this image belongs to class 1. So I can just represent that particular image in terms of this one-hot encoding like 1. Then rest values are 0. If it belongs to second class, then you can represent the 0, 1, and the rest of the values are 0 like this. You will get, I'm just trying to explain the loss function over here. I want to focus on, I want to relate the same loss function in case of image segmentation, right? And how do we solve and what are the problems we will face here? Why we cannot directly adapt actually this network to solve image segmentation. That's what I'm explaining here, right? And as I said, that you will get a 5 set of probability values over here, and this is the target output represented in one-hot encoding. This can be represented as a one probability distribution Y. This can be represented as another probability distribution known as Y cap. Now we're trying to find out the difference between two probability distribution. Now Y cap is a probability distribution, that's the predicted one. Target one, target probability distribution. If you want to find out the difference between two probability distributions, so you cannot use actually mean square error here, because these are not the two single values where you want to see check that whether one or how much one value is deviated from another value. So the kind of loss function which we are going to use to train the model is the cross entropy loss, right? Of course, I mean that's the same concept. I mean, there's a concept known as relative entropy in information theory, right? Which is sometimes known as scale divergence loss. But here we are interested in cross entropy loss. What it does, it tries to just find out the difference between two probability distributions, right? So that is why actually we are interested in this cross entropy loss and how it is computed. Given two probability distributions, just try to find out the distance or the difference between the two probability distributions. Then what is the problem here? The problem you will find in CNN for solving the segmentation task is, I mean, I'm talking about conventional CNN architectures. Always you will find some of the downsampling layers. And that downsampling layer, although helps in reducing the parameters in the model, but is a problem to the segmentation task, because our goal is actually to get an image at the output, not a set of probability values. And that image resolution should be same as the original resolution, because my task is just to classify the pixels. So, okay, fine. Now let us jump to the evolution of this architecture, CNN architectures segmentation task that has been proposed for solving segmentation task, and how it is different from the traditional CNN architectures. Here is the evolution. I will discuss some of the architectures, not all, in this session. But if you're interested, you can just go through many architectures, as many architectures as well that have been proposed over the years. Fast architecture, like you've seen the evolution of the CNN architectures, where you've seen it all started from LeeNet, followed by AlexNet, then VZZ, then GoogleNet, then ReshNet, DenseNet, EfficientNet, and so on and so forth. But here also, the fast architecture, first CNN architecture that was proposed for solving image fragmentation task in the year 2014. This is the fast architecture that was proposed for solving image segmentation task. I'll explain also. I'll get into the details of this FCN architecture in the next slide. So let us now look at the trend, right, of the evolution of the CNN architecture. At the same time, you will find in 2015, you will find two very popular architecture. One is UNet and one is SegNet. I'll explain also these two architectures. And there's one more architecture, PSPNet and DeepLab, which is an advanced variant of this PSPNet. Is also very popular. Then you will find several variants of one architecture, which is known as UNet architecture. That means UNet is one of the very, very popular architecture that has been explored extensively in the literature. So this is the architecture which has been extensively explored, and people have modified these architectures just by introducing some connections, by introducing attention mechanisms into it, and then also people designed the transformer, even the Mamba variant of this UNet architecture. So what it seems that UNet is going to be the backbone for rest of these, models. Like you can see here, everywhere you will find in 2018, you will find this is a very networks, very popular networks actually. So you will find UNet Plus, UNet Plus Plus, Attention UNet, very, very popular architectures. UNet Plus Plus, then REST UNet, you can see where people have introduced residual collections into the UNet architecture. Then you will find how people have combined or how people have introduced dense connections into the UNet architecture along with the attention mechanisms. Then here in 2021, after VIT came into the picture, right, the vision transformer, which has already been discussed in some of the sessions, right? So then people started exploring whether we can use, because people have seen the importance of this vision transformer model in modeling the long range dependencies. I thought, why not use this the concept of the transformer to solve a segmentation task? So here is some set of UNet based transformer architecture. the trans unit, unit R, swing transformer or swing unit, you will find this kind of, and then DS trans unit followed by several such architectures. One thing you can observe here that the unit architecture was initially validated on medical image dataset, and it was published in a conference, medical conference known as MICAI, right? And this is the most popular architecture till that everyone knows, right? Because the paper is already cited almost 1.2 lakh times, like that. So if you look at all these architectures and the data set on which these architectures were trained, most of the data sets, if you look at, are medical data sets. So what it seems, this basically signifies the importance of this task in the medical imaging domain. Initially, it has been validated on the medical data set, but later been adapted to some other kind of computer vision task related to segmentation. Okay, so now let us jump to the first architecture, which was published in 2014, known as fully convolutional neural network. I'll discuss also why it is written VGG16 in parentheses. Now let us try to look at the first architecture, which is known as fully convolutional network. Why the name is so called fully convolutional network? Because at that time, AlexNet was there, LeNet was there, VGGNet was there, and all those architectures was containing fully connected layer or dense layer at the end, if you remember, right? Like AlexNet was having 3 fully connected layers at the end, right? So similarly, BGG was having 3 fully connected layer, having 4096 neuron, and the last layer, of course, containing 1000 neurons because it was designed to solve 1000 class classification problem. It was trained on ImageNet dataset, right? So this was the actually architect. These are the architectures like AlexNet. There's 8 layer architecture, and then VGGNet was a 16 and 19, 2 variants, right? And all these architectures contains fully connected layers. So then what basically they did in FCN, they took the VGGNet architecture and replaced the last 3 fully connected layer by, or the dense layer by 1x1 convolution, right? So now they have removed all these dense layers and replaced these 3 layers with 1x1 convolutional layers. And now all of the throughout the architecture, there is no other layers, only convolution layers are there. So that is why the name is so called fully convolutional network, because it contains the layers which are uses convolution at every layer. After replacing these last 3 layers, right? So what they did, that the last layer, the last 1x1 convolutional layer should have C+1 number of channels, they claimed. Why C+1 and what is C here? The C stands for the number of classes and 1 is for the background. What is our goal here? Our goal in semantic segmentation is to classify each pixel into certain categories. And in this, the data set on which the model was trained was containing 20 classes and 1 plus background. So that is why in the last layer, you will find that the number of channels they have chosen is 21. 20 is for the classes, 1 for the background, right? So the last convolutional layer or last 1x1 layer is having C+1 number of channels, where C is the number of classes. If you're dealing with, let's say, medical imaging data set, where your goal is to simply identify the tumor and rest others will be considered as, let's say, background, the number of classes in that case will be only 1, and 1 is for background. So that means there will be 2 channels in the final layer. So even after converting 21 number of channels, right? Although you have converted these convolutional layers into 21 number of channels, your problem is still not yet solved, because what is required is the output image, right? And that we call it as a segmentation mask. Then what it seems, of course, because you have applied several downsampling layers in VGGNet, and the final layer is only having 21 channels, okay, that is fine, but this will not help you to get an image at the output. So that means we need some operations over here to get back an image at the output. The resolution will be exactly same as the resolution of the input image. So what is the solution here? Of course, the solution is upsampling here. You can upsample these feature maps, and then only you will get this output. So in FCN, they have applied the upsampling operations only for one time to get back the original image, or you can say to get back the segmentation map having resolution same as the original image. So then how did they upsample this particular feature map into this into this, and then followed from this to this map, right? So because the last outputs would contain actually 21 number of channels. I'll explain why, right, in this case. So as I said, that you need an upsampling operation here, and in FCN, they've not applied multiple upsampling operations, right? Or let's say many times you have applied downsampling operations. They've not used the same number of upsampling operations. Rather, they have only used one upsampling operation at the end to get back the original image or to get back the segmentation mask. And we know that upsampling can be done in various ways. You can apply some interpolation techniques over here to solve the task. But rather than using the interpolation techniques which are not learnable, they propose something called as a transpose convolution, right? They propose something called as a transpose convolution. You can see over here. That's the transpose convolution, which is just, you can say, the reverse of the convolution. In convolution, if you apply convolution operation over an image, you'll get just a smaller version of this that particular. The output resolution will be a little bit smaller if you are using actually on-padded convolution, but transpose convolution will help in upsampling, but it is learnable. That is why it is very, very popular. It is learnable. It is not like the interpolation techniques which you have already studied in image processing or signal processing domain, right? So sometimes these transpose convolutions are known as op convolution. It is sometimes in some of the papers is mentioned as deconvolution, but I think deconvolution is not the proper word to use here, because deconvolution has some other meaning in signal processing. So transpose convolution, op convolutions are the two popular names which are used here, right? To upsample, right, the feature map to get back the segmentation map, which is having the resolution same as the input image, and it is learnable. That is why it is very, very interesting one. And that is these are some of the contributions they made in this paper, and they found that okay, because this is the first approach, so they didn't think about applying multiple number of upsampling layers and all, and they have also not introduced a kind of skip connections, which later people have found is a very important concept, right? So this was the idea behind actually this FCN, where you see the same VGGNet architecture which was designed for classification task has been modified, right, and used to solve only the three dense layers. They have converted into 1+1. Last layer should contain C+1 number of channels, and this concept will remain same. Rest of the architecture is what I will discuss today, right? And then, of course, you need some upsampling operations to get back a segmentation mark whose resolution should be same as the input image. That's the fundamental tricks to be used in every architecture. At the same time, there's another architecture that was published in which is known as SegNet. SegNet is also very powerful and very. You can also find out some transformer variant of this SegNet known as SegFormer, right? So SegNet is also equally popular at that time, along with this FCN. So you can see the architecture of this SegNet. It looks very uniform, and you can see this is the first fully convolutional encoder-decoder architectures. You can see here this part is actually the encoder part, and this decoder in this SegNet is just the mirror of the encoder. Just the mirror of the encoder you can see over here. So what they did, so in encoder, they used VGG without FC layers. They did not consider FC layers here. They've taken the whole VGG net architecture without the three FC layers. In the decoder, you will see in the decoder, what they did, the decoder, they have not, of course, in the decoder, you have to use the upsampling operation, right, to get back the segmentation map whose resolution should be same as the input resolution. So then for upsampling, what they did? Upsampling, they have not used transpose convolution. They have not used transpose convolution. Even they have not used any interpolation technique. So they propose an interesting idea in this paper that how to use the pooling indices, the winning indices, during the encoding process, because in the encoding, let's say you are using max pool, so you need to store the winning indices during the pooling, right, of the encoder. So what exactly is this, and how did they solve this upsampling task, and then how did they solve the problem of segmentation, semantic segmentation? I'll explain. Let's say this is the output, this particular, yes, this is the output feature map of any decoder stage which you want to upsample. Let's say this could be the output. Let's say here is the output. Let's say this is the output, and this you want to upsample. Of course, this you want to upsample because ultimately you want to use the same number of layers, or you can say same number of stages, like the number of stages in the encoder. Let's say this particular feature map, or this is the output of any decoder layer which you want to upsample. You need to look at, so as I said, during encoding process, you need to save the winning pooling indices. That means, what is the winning pooling indices? You all know that if I'm applying a pooling operation, and let's say this is, if I'm applying stride as 2, or that means the window size is 2, let's say I'm applying 2 cross 2 and stride as 2 for max pooling, right? Let's say the values are like 1, 2, 8, 5. Here it is 10, 11. I'm just taking any random values here, right? Let's say 12, 15. So, and during encoding process, if I ask you to apply some max pooling operation, what do you do? So you will apply max pooling over this region, because I have chosen 2 cross 2 as the window size, and stride as 2, so that I can directly start from this point. So that means I want to just downsample this feature map from 4 cross 2, 4 cross 4 to 2 cross 2. So this is the winning index. You see, this is 8, right? So this is the winning index, and this index is known as 0, 0. This index is known as 0, 1. This indices is known as 1, 0, and this is 1, 1. You need to store the indices as here. Here is the winning indices, right? 1, 0 is the first, is the winning indices here, and in this case it is 1, 1. I hope it is clear what I'm trying to say. You need to store the indices, especially the indices or the winning indices, while applying this max pooling operation during the encoding process. And that we will use, right, to further upsample the image. And say, basically storing these indices is memory efficient also, right? You can easily store it instead of storing the whole feature map, which will usually require more memory. So now you see, let's say this is the output which is given to me, right, from any decoder stage. I want to sample this output from 2 cross 2 to 4 cross 4, and these are the winning indices taken from the corresponding encoder stage, which is very, very important. You need to look at the corresponding encoder stage, and here is the winning indices for A. So that means A has to put in the 0, 0 position, or 0, 0 position is this one. So B has to put in the 1, 0 position, which is this one. Then C has to put in the 1, 0 position, and D has to put in the 0, 1 position. You see here. And now what you will get is a sparse output. To make it denser, they have used again a set of convolutional layers. You can see here, these blue color layers are actually known as convolutional layers. So because after upsampling, you will get sparse output. To make it dense, they have used multiple convolutional layers. And again, final layer, very similar to the FCN, they have used C plus 1 number of heroes. They have used again in the final layer C plus 1 number of channels. Why C plus 1? C for the classes and 1 for the background. Now let us talk about what kind of loss function we should use in this case. What kind of loss function? In case of traditional image level classification, we know cross entropy is the solution, and we have just now seen that we will get a set of probability values, right? That is known as y cap, and you will be having one target probability distribution, which is y, and then you can find out the difference between probability distributions using this cross entropy, right? It is easy. Now, in case of segmentation, what exactly you are getting at the output? and why you are always demanding the C+1 number of channels. So what I've already said, that for every pixel you will get here a class level. Means what I'm trying to say here is why we need actually this 21 channel, and what it basically tells us that every channel, you can see here, let me just draw here those 21 channels over here. Yeah, let's say the input size is here 256 cross 256, and what I'm expecting from the model is 256 cross 256, and this is, let's say for example, 20 for class and 1 for the background. What it will ultimately give to us, again, a set of probability values, like in the case of image level classification, but the approach is different. So for every pixel here, you will get 21 probability values. You see here, for every pixel, you will get 21 probability values. Earlier, if you are having 21 classes, for every image you are getting 21 probability values. But now, for every image, you will get 21 probability values. And again, based on the maximum probability values, you will decide that which class it should belong to. Let's say the first one, let's say the last value is the maximum one. You can say, maybe if you are representing the last one as a background, then you can say that the first pixel belong to the background. Maybe the second pixel belong to some other object, like this. So every pixel you will get 21 values across the 21 channels, and that is why actually we need 21 channels over here, right? And of course you are using softmax activation function across each of these channels, so that you can just add them up and you'll get the value 1 for across all the channels and for each pixel as well. Now, can you tell me that whether I can, or what kind of loss function I should use here? Previously, we were getting a loss with respect to an image, but here what it seems that we will get a loss with respect to a pixel, because whether each pixel is correctly classified or not, that will tell us the loss function, or that will define the loss function over here. How many pixels are correctly classified and how many pixels are not correctly classified, right? So whether the pixels are correctly classified or not, then what you will do, so you'll be having again some distributions, target distribution, which is already given to us. We have the ground truth. We know the class level. Out of the 21 class levels, we know the correct class level. And now we are getting 21 probability values. Then you need to just find out the difference between these 21 probability values and the target probability values. Again, you can use the same cross entropy rule over here, but the kind of loss function which you will use in this case is actually known as sum of pixel-wise cross entropy, because you are getting loss at the pixel level, and then you need to add them together to get a final loss for a corresponding image. That is why the name is so called sum of the pixel-wise cross entropy, and it is differentiable as well, right? So this is the fundamental idea, or these are the fundamental tricks which you will always use in every architecture. So that what kind of loss function, although this is one of the popular loss functions which we use, but there are also other loss functions like dice loss, IOU loss, focal loss, and all, which are also popularly used in solving while training the segmentation architecture. I hope this. I hope at least you got the idea behind this max. Storing these max pool indices, winning indices, right? This is a bit different from the transpose convolution and the interpolation techniques. Now let us move to the most popular architecture in image segmentation. Semantic segmentation is known as unit architecture. Let me now show you the architecture itself first, and then we will come back that what exactly it is doing and how it is different from the other architectures which I've shown you. It is, again, unit was, as I said, unit was published in a medical conference. That is one of the top conference in medical domain, MICAI 2015, right? So you see here also in unit architecture, you will find an encoder over here. This part is encoder. Again, the decoder is the mirror of the encoder. Sometimes it is known as contracting path and expanding path in unit. And it is very clear that why the name is show called unit, because it is looking like the English letter U. That's why the name is show called unit. And you see here are some of the stages. You see, this is one stage of unit, which consists of two layers, two convolutional layers, followed by a downsampling max pooling layer. Then is another stage, followed by downsampling, another stage, followed by downsampling. Then this is the brief layer, you can say. And then here you can find out the decoder layer, so the stages of the decoder, but you will find some difference. There's a difference here you can observe. Earlier, in architectures like SegNet and all, you will not find this keep connection. You see here, there is a keep connection which has been arise from each of the encoder block to the corresponding decoder block here. And what is the need of this keep connection? And that is one of the contributions they made in this unit architecture. And thereafter, in every architecture, you will find the application of this keep connection in the segmentation architectures, whether it is transformer based, whether it is Mamba based, everywhere you will find out the application of this keep connections and how it basically helps, right? So in early architecture, you will find that in decoder they used to only upsample and followed by some convolutional layers. Here is the stage you can see the upsampling layer. Then there are some convolutional layers, and therefore you will repeat the same procedure until you get the feature maps until you get the segmentation map whose size is equal to the resolution of the input image. Although you will find a difference in the unit architecture because they've introduced on-padded convolution instead of padded convolution. So that's why you will find a difference in the size. But always, what we know that yes, the size should be same, right? But the skip connection basically here, what they're basically trying to do here is, right? So they are taking the output of the corresponding encoder layer during the decoding process, and this basically helps in improving the localization informations. They're not wasting the informations, they're reusing the features that has been learned during encoding in the decoding process, and this helps in improving the localization information greatly. And also they have shown the importance of the skip connection in their paper, that without skip connection how much performance they're getting, and with skip connection how much performance, because this improves the localization, which is very, very important in solving semantic segmentation task. They've also introduced a loss function because, as I said, that this model was initially trained on medical imaging set. So they have observed some problems like especially there are multiple objects present and you need to segment them, so you will find some, let's say, touching components. So how to just avoid those problems, they have proposed some loss function and all, but the major contribution they have introduced in their architecture is how to use this key connection in an fully convolutional encoder decoder approach to solve segmentation task. Later you will find several variants of these unit architectures just by introducing a skip connection, like in residual that people are using residual connections, right? Residual connections, right? And we all know the importance of the residual connection in residual block, which is used in ResNet architecture, right? Because that means you are reusing the features, right? And which will help a better feature flow within the network. At the same time, it tries to overcome the problem of vanishing gradient in residual network. And it also improves the performance as well, right? Because you are reusing the features all the time throughout the architecture. And the same concept that people have also used, right, within the each encoder block called as a residual unit, res unit. You see here, this is the architecture of res unit. You can see here. Now unit is looking like this. This is the U here. And here is set of convolutional operations, as I mentioned, set of convolutional layers, followed by the skip connection. And you will find the same block has been repeated, right, in the encoder as well as in the decoder process. Decoding process, you can see over here, right? And that's why the name is so-called resid-1 connection. Then later you will find that people have introduced several dense skip connections in the unit architecture, better gradient flow, and they call it as a unit plus plus. You can see this is also one of the paper which is published in a workshop in MICAI 2018. You will also find several variants, other variants of unit architecture. People have introduced dense connections within these layers, within each encoder block, and they call it as a dense unit. This is how the evolution of this image segmentation architectures have been posed over the years. Okay. Now let us move to another variant of this semantic segmentation architecture, right? So it is known as actually PSPNet, Pyramid Scene Parsing Network, and the goal was to segment objects at different scales because the objects can have different sizes. So what they observed that FCN could not able to segment the object could not able to segment at multiple scales if the objects are varying in shape and size. So they come up with some idea that how to solve a segmentation task at multiple scales. See, this the idea they have proposed in their architecture. So this is the architecture they have followed, not the fully architecture. I'll discuss the rest of the part in the next slide. You see here, this is the input image which is provided or fed to the CNN architecture like Resonate and all, and then finally you will get a feature map. And then what they are doing, they have introduced something called as a pyramid pooling module. You see here, pyramid pooling module. What it exactly tries to do, where you can find out or you can represent the features at multiple scales. So how is it possible? So let's say this is having size, this particular feature map which has been extracted from using any pre-trained CNN architecture, and the feature map size is, let's say, h cross w cross c. Here h is representing height, w is representing width, and c is representing the number of channels. So then how did they get this kind of results, or what they did basically pooling at multiple scales. So this is the output of a global average pooling that we all know that if you apply a global average pooling over each of the channels, because pooling doesn't reduce the channels, only it reduces the spatial size, or you can say the spatial resolution of the feature map. So this is the output. If you apply this global average pooling over here, you'll get 1 cross 1 cross C, because for every channel you will get a single output because you are taking the average over each of the pixels or each of the values over here. Similarly, the other outputs would be 2 cross 2 cross C. That means the same H cross W cross C is now pooled to 4 different types of outputs, like 1 cross 1 cross C, 2 cross 2 cross C, 3 cross 3 cross C, and 6 cross 6 cross C. Right? And then what they're doing and why actually they're doing this, because they want to represent the output or the features at various scales. And this will help us in segmenting the different objects at various scales. So what they're doing then, after getting these pooled outputs, they are applying convolutional layers, or 1 plus 1 convolutional layers, just to reduce the dimension of the channels. That means after applying the pooling operation, as I said, if the number of channels were C, now it is going to be C, 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 and C. So they have just tried to reduce the number of channels from C to CY. And then what they are doing, they are applying some upsampling operations over here, because ultimate goal is very simple, to get back to the original image resolution size. And what kind of upsampling operations they are applying? They have applied here bilinear interpolation technique. And then what they're doing, bilinear interpolation techniques over these 4 outputs, and then they have concatenated their output with the H cross W cross C over here, which is the output of any CNN architecture like Resonate and all here. Then after concatenating these outputs with the previous feature map, which has been derived from Resonate, let's say here, then what they're doing, they're again applying like some segmentation head, right? I can call it as a segmentation head, where we're applying some convolutional layer to, and which that will lead to C plus 1 number of channels. And then maybe if some upsampling are required to get back to the original size, some upsampling will be applied over there, right? So concatenated features are passed to the upsampling and convolutional layer to generate the output segmentation map. Here, always we need the segmentation head. Sometimes we call it as a segmentation head, which usually consists of a 1+1 convolutional layer with C+1 number of channels, right? And C+1, we've already discussed it. A very similar architecture you will find in the literature known as deep lab, and several variants of deep lab. One of the variant which is very popular is known as deep lab v3. So what they did, so instead of using this pyramid pooling, they have proposed ASPP module, which is the Atlas-based pyramid pooling approach, right? So which is a bit different from this pooling approach, but almost all the concepts or almost all these design choices are same, except the pooling module, right? For solving this deep learning, but to design this, especially this deep lab architecture, right? I mean, in decoder also they have made some modifications. In decoder also, instead of using simply 1+1 convolution over here, they've also made some modifications. In even deep lab v3 also, they have made modifications in their decoder part, and they have claimed that deep lab v3 variant is better than deep lab version, deep lab other variants. If you want, you can also go through that, because deep lab v3 is also a very popular architecture solving semantic segmentation task. Later, with the advent of these attention mechanisms, attention mechanisms are right now the integral part of any advanced CNN transformer architectures. Also, you have seen there's an attention mechanism known as self-attention, very, very powerful, right? And that is why we are actually getting, or you can capture the global relationship, a global contextual relationship within the feature map, right? That's the main reason behind it, and why VIT is really performing well. And several, similar to that, in computer vision, especially, there are different types of visual attention mechanisms that have been proposed over the years. If you go through this literature, you will find the set of such attention mechanisms that have been proposed over the years. And some of the popular attentions are like channel attention, spatial attention, combinations of this channel and spatial attention. The goal is very simple, actually, to focus on the important part of the, focus on the crucial part and suppress the other irrelevant parts, actually. And this attention mechanism will make sure that my model is really focusing on the important part, and it will try to capture the important information only from those parts, and it will not focus on the other parts. That's the goal of attention mechanisms, and it is very natural to the human vision system, right? We usually look at the crucial part while taking some decisions. So similarly, the attention mechanism will help the model to look at the important part and suppress the other parts. Fine. So inspired by the success of these attention mechanisms in NLP as well as computer vision domain, people have also introduced attention-based unit architecture. So this is one of the very popular unit or early unit architecture where attention was introduced for the first time, right? So you can see again, the structure is the same, the backbone is the same, but they have introduced something called as an attention gate, right? And they've got good performance compared to the standard unit architecture, and they have also proved, quantitatively, they provided quantitative results as well as qualitative results in their paper. If you're interested, you can just go through these papers and you can see the results. Again, it was introduced, it was validated on medical image data set. So here is another variant of this another variant of this unit architecture known as RES Unit++. It's also one of the popular architecture. And here you will see the application of both, the uses of both the residual connection as well as the attention mechanism. You can see over here. Here's an attention mechanism they have introduced, and the very popular attention mechanism known as squeeze and excitation has been introduced over here. Squeeze and excitation is a channel attention mechanism. You will find the application of both residual connection here. So this skip connection will be always there if you are using unit backbone, right? This skip connection is really useful, right? But they have additionally used these skip connections within each encoder block or within each decoder block, this architecture. And they called it as a RES Unit++. Again, it was applied to some medical image analysis task past. Now, next, of course, you will find several other variants of unit architecture. If you go through the literature, I cannot discuss all those architectures here. But now let us also look at some of the transformer-based unit architecture, which are quite popular for solving semantic segmentation task. And as you all know that why this vision transformers are very popular nowadays. It has several advantages, and there are also some weaknesses of these VIT models, right? We all know that vision transformer has got a lot of attentions in recent years to solve a wide variety of computer vision tasks, classification, segmentation, and even in detection also you will find a lot of approaches. Transformer based is very powerful technique actually, because the latest architectures, the latest foundation models, whether it is SIAM or there are some other foundation models that are available, right, which usually tells us that yes, transformer is the backbone which are currently being used. That's the current state of the art approach actually in computer vision, right? So in every foundation model you will find the application of this vision transformer, and it is really popular because of its capability to capture global contextual information, because CNNs are actually good at extraction of the local information, because convolution to a local region, right? So the receptive field is really limited in case of convolutional neural network. Even if you have multiple number of layers, even if you are having 100 layers, still it has a limited receptive field size. But this vision transformers are really useful in this case while extracting this global informations, right? But again, VIT has certain limitations because it demands huge computational requirements, and it is also it is also demanding huge amount of data and all. So we'll discuss some of the limitations also later on of this VIT architectures. But now let us look at whether VITs can be adapted to solve semantic segmentation task or not. There are a couple of such architectures actually available in the literature. I've just chosen two for this particular session. You can also go through some other architectures if you're interested in, right? So this is one of the architecture which is proposed in WSCV 2022, and the architecture name is UNIT R for the transformer here. I mean, whether UNIT can be adapted, or whether this kind of backbone can be transformer based architecture or not, and that is what is all about this unit architecture. You can see. So I think there was a session on vision transformer or transformer where you have seen that how images were initially divided into patches, then followed by linear projection, positional embeddings, and then followed by the transformer encoder, then the decoder block for solving this segmentation task here. So how it usually looks like is this. So this is a whole architecture actually for this unit R. So instead of sending it to some convolutional blocks over here, you need to send actually, you need to first convert these images into multiple patches, because it works on the patches, right? Otherwise, the computational complexity is going to be really high, right? I mean, the way this transformer has been applied to natural, I mean, this NLP domain is something different, but here initially it has been decided that to first divide these images into multiple patches, and then there are over the patches only we can apply this transformer encoder and all, right? So here also the same procedure they have followed, and they got the patches and they have got the encodings, or you can say different embeddings from these transformer layers, right? Of course, it contains multi-head self-attention mechanism in the encoder, right? And then they have used a set of convolutional layers in the decoder block to get back the original, you can say the original input size, or you can say the original input resolution. But this was initially validated on 3D volume data, because you can see here is the MRI data, which is usually 3D in nature. It was initially validated on 3D data, but if you are interested, then you can also modify this architecture into a two-dimensional, for solving two-dimensional image segmentation task. So here is another architecture which is quite popular, known as trans unit. Again, the same transformer concept has been used over here, but in this architecture, they have directly not applied transformer, or you can say self-attention over the image patches. Rather, they have first applied some CNN layers. Then from those CNN layers, they got the patches, and then they applied the transformer layer. And again, in the decoder, you will find, of course, find the upsampling layers, and all these architectures actually, except this SegNet and FCN, except this SegNet, you will find in every architecture, or PSPNet, you will find in every architecture people are using transpose convolution. Here UNIT also transpose convolution, and all the variants of UNIT are also using transpose convolutions upsampling purpose, right? But instead of directly applying this transformer over the image patches, they have first extracted the patches through some convolutional layers, and then applied this, you can say transformer layers. You can see here is the standard transformer layer which is used for solving any vision task. That's the multi-head self-attention. Here is the skip connection, followed by some of the MLP layers like 1 cross 1 convolution and all, right? And then you can see over here, they have also used a skip connection. And for skip connection, they're connecting this skip connection with the output of different convolutional layers with respect to the decoder layers over here, right? Again, this was validated on medical imaging data sets initially and later been adapted to other tasks. So here is a set of loss function which are currently being used for solving or for training the segmentation architectures. Of course, deep learning based segmentation architectures, which we have seen. So there could be different types of loss functions, which are pixel level loss functions like binary cross entropy if there are two classes, otherwise cross entropy. And if there are number of classes, if there are number of classes available in your data set and which you want to segment, and they are not properly balanced, they are imbalanced. So what you can do is you can just go entropy technique or focal loss kind of technique that will help you in dealing with this class imbalance problem in the segmentation task, right? And the dice loss is one of the very popular kind of loss. So dice is actually a performance measure which is usually used to evaluate the performance of the segmentation architectures, but dice loss has been introduced to mimic the behavior of this dice measure, and which is really quite useful compared to cross entropy, right, for solving a variety of semantic segmentation tasks. And you will also find that people have also developed something called as a boundary-based loss function, because boundary plays a very, very important role in segmentation. They have also proposed some boundary-based loss functions. And this compound loss function is just a combination of, let's say, people have, in most of the cases, you will find that people have combined this cross entropy and dice loss together. This is a very common combination. I mean, you can say common combination you will find in many of the recent papers, that people are combining both cross entropy loss as well as dice loss together. And while combining, you can give importance to cross entropy. Maybe you can just give, let's say this is L1 is for cross entropy, L2 is for dice loss. So you can just provide just alpha plus L1 plus 1 minus alpha into L1 minus alpha into L2, where alpha varies from 0 to 1. You know that, right? So this you can just provide a weight, right, based on the you can say priority, or you can say importance of this loss function. And that also you can change, or that also you can make learnable to check which alpha value is giving you better performance. I mean, combination of the loss function in case of the compound loss I'm talking about. Here's a set of performance measures which are commonly used to evaluate the different segmentation architectures. Accuracy, I have not mentioned accuracy, sensitivity, and all. Sometimes accuracy is not a good measure, actually. Right? Accuracy is not a good measure if you are dealing with only a binary segmentation task. Right? In case of binary segmentation, I'll explain why accuracy is not a good measure. Accuracy, what basically it tells us how many pixels are correctly classified, because it's a pixel level classification task. How many pixels are correctly classified out of all the pixels in the image, right? But in case of medical imaging, what you know, that most of the pixels and some of the pixels belong to the tumor region, and most of the pixels belong to the background region. Even if your model could not able to detect a single tumor pixel, but still it will say that your model is 90% accurate, which is wrong, right? So you cannot consider accuracy as a measure in all the cases. If it is a multi-class segmentation task, then probably, I mean, where you need to you can say segment all the pixels into certain class, then in that case probably accuracy is going to help you. But in case of this binary segmentation and all, this accuracy is going to fail, right? It doesn't give us some important information to us. So in that case, what if for this dice coefficient or this IOU in the intersection of a union, where you can find out the overlap between the ground truth and the output segmented image, because you will get some output segmented mask and there'll be some ground truth, and you can have a comparison among these two. And intersection of a union is also one of the very important measure over here, right? There are also other performance measures which you can go through. If you go through the literature also, you will find, right? But these are the very popular performance measures which we usually use to check the performance of a particular model, right? So let me now show you some of the case studies. I mean, only I'll show you one case study, right? Then I'll jump to the foundation model. I'll tell you that what kind of problems we are encountering, right? While solving some segmentation task, and why we are interested in this foundation models, right? Now let me show you some of the case studies on polyp segmentation. Let me first explain what exactly polyp is. This polyp is again a growth in the inner wall of the colon, and the polyp is the growth which usually leads to colorectal cancer if left untreated. So that means if these polyps are not detected at an early stage, or if they are not removed, it leads to colorectal cancer. And colorectal cancer is one of the most common cancer worldwide, and its rank is third among all types of cancers. And it all originates from the polyp, which is the growth, as I mentioned over here. What is the problem? What is the problem? And how it is being detected? It is being detected using the colonoscopy process. That's fine. But then what is the problem? The problem is the miss rate of the polyp detection is really high. It is 6 to 27%, right? And sometimes it is very, very difficult to identify the polyps, even by the experts. And that is why the miss rate is around 27%. And as I said, that if some of the polyps are not detected at an early stage, then that may lead to colorectal cancers. So people are trying to develop their own machines. Till date, there is only one machine available. I mean, that's of course AI based. So you can also contribute to this. You can contribute to identify. I mean, there are actually approaches which are available. There's one company which basically developed recently an architecture, AI based, of course, deep learning based, which usually detects the polyp, but it cannot segment the polyp. Like segmentation is even more important. Why? Because it will provide you the boundaries, accurate boundaries to the clinicians, and that will help them to easily resect the polyp. So what are the challenges here? The challenges are actually here of different types. So there could be multiple polyps that present, and sometimes, and most of the times, the polyp varies significantly in size, shape, and color. Sometimes the texture of the polyps looks very, very similar to the surrounding tissues. You can see here. Here is a polyp actually. It's a polyp which is difficult to identify. You can see over here. Polyp difficult to identify because the texture is very close to the texture of the background, right? And usually these kind of polyps, even I will show you some complex cases where the mix rate is really high. And there could be multiple polyps. So not all growths are polyp, right? But we need to identify those growths which are only polyp. And also you will find sometimes that polyps are covered with mucosal fluids and blood. It is also in that case also very, very difficult to identify. And as I mentioned, the most difficult part is most of the time you will not find clear boundaries of the polyp, which is very, very important for the segmentation task, right? So you find indistinct boundaries, right, for polyp, which is really, really difficult to identify. These are sometimes known as flat polyps. You will not able to find, right, whether there's a polyp or not. And the presence of the multiple polyps also in a single frame creates absolutely. So then can we solve this problem with the help of these advanced CNN transformer architectures, right? So we started this work 2 years back, actually, two and a half years back. So when we got this problem, so then we you can see here. This is the first approach actually which we proposed, known as MCTNet, Multi-Scale Convolutional Transformer Network, to solve this task actually, to solve or to segment the polyps. So the idea behind this architecture was, I mean, we have seen the importance of this convolutional neural network or CNN-based architectures like unit-based architectures. This is again a unit-based architecture. And we have also seen the importance of CNNs at extracting the local informations, although the traditional unit architecture fails to segment at different scales. That was the main contribution which we made, that can we segment at different scales. So again, for different scaling, I can use even the pooling operation, which the PSP-net uses, but we have not used those pooling operations. Rather, we have extracted the features at different scales. So features at different scales can be extracted by simply applying multiple filters having a different sizes. Like let's say if I apply 1x1 filter, 3x3 filter, 5x5 filter. But if I apply large size filters, the number of parameters are going to be really high. So instead of using traditional convolutions, which usually takes large number of parameters to implement the large size filters, what we have used is a separable convolution. You can see over here, separable convolution will drastically reduce the number of convolutions while tries to extract the features at different scales, like 3 cross 3, 5 cross 5, and 7 cross 7. Then we concatenated the output. This is the block actually. This is the convolutional block which we have used in the encoder, followed by an attention mechanism to focus on the important regions and to suppress the other regions. And this process has been repeated in the encoder process. But in decoder, of course, we are using the skip connection that has been introduced in unit architecture. But the skip connection, in the decoder block, we have used a transformer block. So usually, in transformer, we use self-attention block, and self-attention originally, the vanilla self-attention architecture is actually spatial attention based. It can capture the global relationship along the spatial dimension, but it cannot capture the global relationship along the channel dimension. And that was also one of our contribution here. So we proposed such a self-attention mechanism which can capture the long-range dependencies, or you can say the global contextual information along the spatial dimension as well as the channel dimension, like the channel dimension and the spatial dimension I discussed, right? In case in visual attention mechanisms. So here is the set of, you can say, output. The decoder is fully a transformer architecture, and the encoder is fully CNN architecture, where we have just combined the strength of the convolutional layers or convolutional neural network and transformer together, and that is why the name is so called convolutional transformer. It has the properties of both convolution and the transformer together, and that is why actually it is performing well. And this was actually one of the highlight paper in 31st International Conference on Image Processing 2024, and this work is with my master student Niladri Chakravarti. So here is some of the output quantitative results we have achieved on 3 different data sets. Right? I'll also discuss about the limitations of this approach. So why actually we shifted from designing the model from the scratch to use the foundation model, or to adopt the foundation model to solve the same task. I will explain. Right. So here is just some of the outputs. So as I said, the most important performance measures are like mean dice and mean IOE here, right? And we have just compared with the architectures which I've explained, I think today, almost all the architectures I've discussed today. UNet, SegNet, deep lab, I've explained PSPNet, which is a variant, of this deep lab. REST unit I've discussed, attention unit I've discussed, REST unit plus also I've shown you, and unit are also we've shown you. So out of all these architectures, what we have found that our model is consistently performing better results in across all the data sets. And we've also seen the importance of all these modules, whatever I've explained through the ablation studies. That is fine. But here is a qualitative results which we have obtained from our model across 3 data sets. Right? You can see there are some complex cases we have chosen. Here is the input. The first column actually represents the input images. The last column represents the ground truth provided by the doctors. And the second last is the output which we have got from our model. You see, so the output which we have got from our model is very close to the ground truth compared to the other approaches which we discussed today. Sometimes you look at the second last row here, right? It tells us there are 2 different polyps, and most of the popular architectures could not able to detect the 2 polyps in their accurate boundaries. But you look at our result and look at our results. We have got 2 polyps, right, as well as the accurate boundaries. Similarly, you can look at other examples. You will find that our model is more accurate compared to the others, and we were happy at that time that our model could able to, beat the other popular architectures. Later, when we met with the doctors, and doctors said, and we came up with this idea, sir, we've got better performance. So now I think we can validate it on some real data. So then when we started actually deploying, or we can say when implementing or validating our architecture on scene data collected from different devices, collected from different patients of different demographic regions, then it suddenly fails. And it is a common problem that the generalization capability of these models trained on very small data set is really limited, right? So then what you will do in that case? how to improve the generalization capabilities. That was the idea time we had, that how to improve the generalization capability, because our ultimate goal is to train the model, implement or you can say deploy the model on the on-scene data set or in any data, and it should perform well. So that means the feature learning capability has to improve, right? So it should be independent of these devices, patients, and all different regions and all. So then we found that the foundation models like segment anything model. I don't know how many of you have used this model or have heard about the name of the foundation models. Segment anything model is a very, the first kind of foundation model. So when I say foundation model, what does it mean? So foundation models are usually trained on a very large scale data so that it can be adapted. And the goal is to actually adapt this kind of model in future to solve a wide range of downstream tasks. That was the goal, to design this foundational model. And now it has become a practice in computer vision, in NLP domain, to design the foundation model. Now you have seen several foundation models like GPT series, like BOT series. Those are also foundation models in NLP domain. And the first foundation model in the in image segmentation domain is known as segment anything model. I'll discuss what exactly is the segmentation model and how to use the segmentation model to solve, let's say, the polyp segmentation task, which you have done. And why this kind of models are very popular? Yes, it can be adapted to wide range of downstream tasks. That is fine. At the same time, it is these models are very well known for their impressive generalization capabilities on the on-scene data set. And they have also shown this in their paper that their zero-shot generalization capability is really impressive compared to the task-specific models which I have just now shown. So the kind of architecture which I have just now or which we have developed is very specific to this task, right? And that is why it is not actually working well on the on-scene data, although they are from the same domain. Although the domain is the same, still it is not working. Just think about it, the domain is different, how this architecture is going to behave, right? So always you need fine-tuning and all. But generalization performance has to be improved. So that is why this foundation models came into the picture. And this is the first, SAM is the first foundation model. I hope it is clear that why there is a need of foundation model. And the first foundation model, as I said, was proposed in ICCV of 2023, known as segment anything. So this segment anything model is a very popular foundation model, as I said. It introduces promptable segmentation task. I hope you all know what are prompts right now, right? Because everyone is using Chat GPT and all. So this is the promptable basically they introduces something called as promptable segmentation task, right? And which in early models, what we have seen, that the models which you have seen, right, earlier, which usually takes input as an image, then we pass that image to the model, then you will get a mask over there, right? And you'll be having some ground truth, and accordingly you will fine tune the model and you will refine the mask, right? That is what we are doing. But as I said, the SAM introduces promptable segmentation task. So the goal here is not only take image as an input to the model, but also a set of or a kind of prompt. And the prompt could be here a set of points, or the prompt could be that will guide the actually segmentation process to get a valid mask, right? And then the prompt could be a bounding box. The prompt could be a mask itself, which will also help in refining the mask at the output. The prompt could be a text, right? So image along with prompts will be passed to the model. Then it will provide us the valid mask. When I'm saying valid mask, what does it mean? It will at least segment one of the objects accurately out of all the objects. That is what is known as valid segmentation mask over here. So the three contributions they've made: one, how to introduce something called as a promptable segmentation, and that prompts, how these prompts will guide you in getting a valid mask all the time, right? And that is why the name is so called segment anything. It can at least give segmentation of some of the objects that are present. It's not possible to get all the objects, right? So that was the main idea. And the task is simply was one of the contribution from table segmentation. Yes, in model level also they have contributed. You can see here. Here is the image. Here is the prompt, and that image will be initially passed to the this representation actually is in the abstract level, but I'll explain it later on. Okay. So this image will be passed to a pre-trained image encoder. This could be a vision transformer model, and this vision transformer model will give us some embeddings. Those embeddings, along with this prompt embeddings, right? This basically, if you are passing some box here, bounding box, or let's say points, or let's say mask, so that has to be first converted into some embeddings through some process I will explain in the next slide. And then those two informations will be passed to lightweight mask decoder. It has to be lightweight actually, right? So basically in mask decoder, again, is a kind of transformer, lightweight transformer, where we are only performing some set of attention mechanisms like cross attention mechanisms to get a valid mask. This is the second contribution in the model level. In data level also they have contributed in this paper. Because what you all know that there is no such data set available at that time having billions of the images along with their mask. So they proposed a data engine where they have basically, right, said that yes, how to generate the mask and all. So the data level also they have contributed, in the model level they have contributed, in the task level also they have contributed. And this is the first model. And also later you will find some other variants of the SAM, which has been extended to videos and all. Then finally, what is encoder here and what is decoder here? Let me just show you. What is encoder and what is decoder here? Here is the encoder. This is the input image, which will be fast head to an image encoder. An image encoder could be any pre-trained fit model, right? So it could be, originally it was been actually applied on mask, auto encoder, this pre-trained VIT model. So it will generate some embeddings over here. And now you look at, this is the decoder part. So the image encoder will generate some embeddings. If you are using mask as a prompt, then you can use some convolution operations and just combine those two embeddings, send it to the decoder. If you are not using mask, if you are using point, box, and text, so then in case of box and point, you can just use positional encodings, like in case of transformer, which you have seen, right? You can use those positional encodings as their embeddings and then send it to the mask decoder. And that mask decoder will help to get some mask or valid mask. Of course, there'll be some upsampling operations over there. Self-attention mechanisms, cross attention mechanisms. Why cross? Because you have now two embeddings. One is from image, one is from prompt. You want to have, right? You want to just fuse those informations, and the fusing those informations can be done in one of the ways. And one of the ways is actually this cross attention. So if you are using text prompt, then you can use the you can use the encoder, the text encoder that has been used in CLEAP. CLEAP is another very popular foundation model known as visual language model. If you are interested, you can also go through this paper. This is a very popular, the most popular visual language model till date, right? Again, a foundation model, right? So that means ultimately what we are trying to do here is we want to generate some image embeddings and then some embeddings from the prompt. Then we want to pass these two together to the mask decoder, which can, right? And this prompt, main goal of this prompt is to just guide in generating a valid mask, right? So here is this mask decoder should be a lightweight fast two-way transformer. This is how actually the decoder, the mask decoder looks like, right? You can see here the image embeddings having size 64 cross 64 cross 256, right? And here is the prompt token, so the prompt embeddings. Now it has been passed to two cross attention mechanisms here. One is image to token attention. This is considered as token over here. Now another one is token to image. Then this has been passed to another attention, token to image attention, then followed by some of the MLP layers, upsampling layers to get the mask, the valid mask. That's the job of this SAM decoder over here, right? And now SAM has become the state-of-the-art approaches for solving the segmentation task, because it has achieved the state-of-the-art performance. It is very difficult to beat the performance of the SAM by developing your own architecture and train it from the scratch, because it has been trained on a huge data set, right? So then, when we started working on the SAM 2 years back, 2.5 years or 3 years back, so then we found a lot of difficulties while adapting the SAM. While adapting the SAM, we found a lot of difficulties while adapting the SAM to medical imaging domain, right? So what are the problems we encountered while adapting the SAM to solve the same polyp segmentation task, right? So SAM is not performing well when it is directly applied to the medical imaging domain. It is only because the lack of the domain specific knowledge. SAM is not having domain specific knowledge. So later people have developed something called as MAD SAM, right, which was trained on millions of the medical images, right? You can also go through those papers, MAD SAM, if you're interested in solving the problems. But we are not interested in adapting that MAD SAM, right? Because MAD SAM was already trained. I mean, at that time also, we were also planning to use this, how to use the segment anything model or SAM. This is the first limitation which we observed, that it is not performing well. The second problem which we have observed, that fine tuning of SAM is also a time consuming process, and it leads to high computational cost, and it also demands high memory requirements. What does it mean? Because we know that transfer learning is the easiest solution to use any pre-trained architecture. So then why can, then of course, we can also use transfer learning approach over here, because the segment anything model demands a huge number of parameters, and it requires huge number of parameter tuning. So direct fine tuning is not going to help us. Then what is the solution here? The solution is here actually adapter based fine tuning. If you can design a small module known as adapter, right? And if you can fine tune only the adapter which can communicate with the SAM encoder, or let's say the layers of the SAM, which is usually, as I said, the feed blocks, that would be really helpful for us. Instead of fine tuning the SAM directly, we can fine tune the adapters, and then that adapter will communicate with that. So adapter has become again an integral part of recent, or you can say advanced architecture, deep learning architectures. And you might have also heard about adapters like LoRa and all that has been used for solving even initially the NLP problems and all. Then we came up with this idea that which is known as actually SAM Mamba, right? Where we have actually multiple contributions we have made in this paper, and this was actually accepted in WACB 2025. And the problem statement is still the same, that how to improve the generalization performance of the segmentation task, right? That means we will train the model on few data sets, and then we will test the model on the data sets or on scene data sets collected from various different patients, and the images should be captured from different imaging devices. Of course, from different place, also different demographic regions or different hospitals, you can say the patient should be from. So then we will see whether it is performing well or not compared to the traditional approaches. I'll show you some of the results, state-of-the-art results, which we have received. Okay. If you just look at this architecture, I'll not go into the details of this architecture. So codes are also available. The paper is available. So if you just type it in Google, so you'll get this paper and you'll get the details of this paper. Right? I'll just give you the idea that what we have done and what was in our mind while developing this architecture. As I said, that we were not planning to fine tune because we are not having those, GPU facilities at our institute. So we are having limited GPU. So we could not able to actually train the model from the, we could not able to fine tune this heavy model, this heavy SAM encoder, because the decoder is the lightweight part. But it is only because that they have used, this beat blocks, especially feed architecture in the encoder. So then we thought of why not to then introduce an adapter-based fine-tuning here. And there was a paper actually, VIT adapter, which says that adapter can be easily used to fine-tune the large models for dense predictions. So inspired from that paper, we applied this within the SAM encoder block. And then in addition to that, we have also proposed a Mamba prior block. So Mamba is again an advanced computer vision model, right? Similar to the vision transformer, but very, very popular for capturing long range dependencies, which usually even VIT does, but at a linear complexity. right? And it is a state space model actually. So again, Mamba has several variants. There are Mamba Vision Mamba, different types of models you will find. Originally designed to deal with one-dimensional sequence, later has been extended to two-dimensional sequence. If you go through the Mamba paper, you will find that it has been introduced to deal with the images directly. So inspired by the success of this Mamba architecture, we plan to use some prior block so that we can pass some domain knowledge to the adapter, and that will be communicated to the SIAM encoder. That was the main goal, right? So that you see here, this Mamba prior is trying to get some information, of course, trying to learn the features at various scales, and then process it through the Mamba block to get the better feature interactions. And then we are passing the same to this adapter. And adapter is nothing but a sequence of two cross attention blocks over here. You can see, right? And this is one of the contributions which we made, that we will apply a Mamba prior block, because without this Mamba prior block, we could not able to get a better performance. Although we are getting, of course, state-of-the-art performance, but you throw this Mamba prior block, we got even better performance, because we are sending some domain knowledge into the architecture. The second contribution which we found, from where we will get these prompts, right? Because prompts, it is a promptable segmentation task, and getting the prompts is always a difficult task during the inference time also, because we can't always give the prompts during the inference time. Then what we thought, why not to generate the prompts from the same model, right? What we usually did is, here the training is happening in two stages. First, we only train the encoder part, and then tries to generate some of the pseudo mask, and then those pseudo masks are used as a prompt encoder, the SAM decoder, and then we are again using another training stage where we are training the encoder part as well as the decoder part. That's the, again, one more contribution which we have made over here, how to remove or eliminate the need of manual prompt or manual prompt generation, right? That's why, I mean, we have actually we can say propose this kind of approach where you can generate our own mask, right, and then send those masks as a prompt to the SAM decoder. That is another contribution. If you are really interested actually in this paper, and if you can just go through this paper, and this actually the code is available, and if you are also having doubt, please drop an email to me. I'll get back to you. No problem. So let me now show you some of the interesting results which we have got in comparison to the state-of-the-art approaches on the same domain. Right now, you see, as I said, that we have validated these approaches on the scene dataset as well as on the on-scene dataset, right? So these are the results on the scene dataset. That means these are the dataset on which we have trained our model, and these are the dataset on which we have again tested our model. Right? But the train set and test set are of course different, but from the same dataset, right? So here you see the comparison with the state-of-the-art approaches. All are actually starting from UNet to our model. On the scene dataset, even UNet is not performing bad. UNet is also performing well, although we have got the performance around 92, but UNet is also getting 81 performance on the scene dataset. So similarly, we have taken 6 different performance measures, and these 4 are the performance measures very useful for even detection tasks. But here also we have chosen, because boundaries is very important. That's why we have chosen these 4. So now let me show you the results which you have achieved on the on-scene datasets. These are the CVC 300 and CVC colon DB datasets. Are not, we have not trained our model actually on these datasets. These are the results on the on-scene dataset. Now you see the results of our approach. This is the fast, actually SAM-based approach on this particular domain of research. You can see the results which have been achieved on the on-scene dataset. You see, from UNet is 71, and here it is 92. You can see it is 51 in case of the CVC colon DB dataset by UNet, right? And there are other architectures, of course, and our architecture could be able to achieve 85. So this basically signifies the importance of the SIAM kind of architecture or foundation models improving the generalization capabilities. I'll show you some of the qualitative results now. Very complex qualitative right, you can see examples, right? You see here are some of the images. You see, it is very difficult to identify the polyps. These are some of the complex cases. And the second case, if you look at the second case, it is very easy to identify, let's say in some of the cases, but in the second case, it is the polyps are usually missed. Why? Because there are two polyps. Here is the image. Here is the ground truth provided by multiple doctors, right? Here is one, and this one is usually missed. You see here, this one. And now if you look at, these are again on the seen data sets. Seen data sets, right? Now if you look at the results obtained by UNet plus plus, most of the architectures could not able to identify the second polyp, whose texture is almost similar to the background texture. But it is the output of our approach. Mamba, you see, it could able to identify two polyps, which are really difficult to identify. These are difficult cases I'm talking about. Here is the qualitative results on the on-scene data sets. So for on-scene, actually, we have chosen 3 data sets, although I have shown the results of 2 data sets. I mean, quantitative results of 2 data sets, but we have chosen actually 3 data sets. Now let me show you some of the results over here. Again, this is the input image. This is the ground truth. You see, look at this particular case. Very, very difficult case. This polyp, there are 2 polyps actually. This is the ground truth you see. Now, if you look at any growth over here, it is difficult to find because these are known as flat polyps. It is very difficult to identify whether there is a polyp or not. Right? You see the output. UNet could not even able to identify whether there is a polyp or not, like us. UNet plus plus could not able to identify whether there is a polyp or not. You see here the results. Some of the architectures could not able to identify there are 2 polyps. There are some architectures could able to identify, yes, there are 2 polyps, but the boundaries are not precise. Again, MegaNet, the state-of-the-art approaches could not able to find out that the distinction between the 2 polyps. Even our SAM Mamba could not able to, although this polyp is quite good, but the boundary of this polyp is not clear. It's not accurate, right? So that means what we have seen in case of weak boundaries. So this scenario is known as actually weak boundary scenario, or where the boundaries are not distinct, are not clear. So in that case, we found that our model fails. Our model could not able to provide accurate results. So then we come up with another idea known as SAM-MAGU, and this was actually accepted in MICAI 2025, where UNet was published. So this was also luckily we got an oral presentation for this conference, and our paper was a highlight paper in that conference, MICAI paper. So this was again now with some of my students, right? So here the concept remains the same. I mean, the architecture still remains the same. I mean, with the SAM Mamba which I have shown, but the major contribution lies in proposing a module known as Mamba guided boundary prior module. So here our goal is to actually enhance the boundary informations while segmenting. So then what was the idea? The idea was very simple. After getting the embeddings from these BIT models, is there any possibility to inject some boundary informations into these embeddings? That was the goal. So then what did we did? We choose this particular component will not be used during inference time. This yellow color block is known as MAGU, right? This particular block is only, this boundary distribution component is only going to be used during the training, right? So what is our goal here? Our goal is to just send the informations or the distinction between polyp and the non-polyp regions and inject those informations via a distillation approach through this distillation approach to this actually the final embeddings of this SAM encoder. And that was the measure actually, you can say, contribution which we made here, right? And the rest of the contributions are still the same. The way we have sent the prompts is still the same, and the adapter still we are using here. Only we have made modifications to this prior block. Earlier we used only one-dimensional Mamba, but later we combined one-dimensional Mamba with two-dimensional Mamba, which is really useful for analyzing, or you can say capturing the long range dependencies over the feature map itself. So that is why we have seen the 2D Mamba we have introduced here. So 2D Mamba is actually really performing well. Also, we have proved it through these Ablason studies and all, that whether 2D Mamba is really giving good results or not. This is just performance improvement, but this was the main idea, that can we improve the boundary informations, right, in case of weak boundary polyps. And this, if again, the codes are available, and if you are interested, then you can just go through the paper. The idea is still the same as I mentioned, but only this component is different. And this component is not going to be useful because this component uses mask. You see, this component uses ground truth mask versus polyp and non-polyp. And then are actually using this information along with this embedding information, because we are making a distillation, and then we are performing a cross attention over here, right, to send to get the final information just before the distillation. And the most important thing here is we are only going to use this module during the training time, because during the training time only we are having the mask. We will not be having any mask, so this component is not going to be useful in inference time. That means it will not even increase the time required during the inference time, because it is not going to be useful during the inference time. So now let me show you the results which we have obtained after introducing these two blocks into our previous architecture. You see the results which we have obtained for the same case. Now let me just zoom it. The same case. Now you see the result of the same case, the most challenging case from the cities data set. You see here. This is the ground truth, and this is now the result which we have obtained. You see, there's a huge performance improvement, right? The boundary, even in the weak boundary cases. You see here. This is the output of Siam Mamba, where the separation between the two polyps are not clear, the boundaries are not clear. But now the separation is also clear, the boundaries are also clear. It is only because of this BDC component of which we have introduced in this architecture. So there are also a couple of other case studies. I mean, a couple of other segmentation tasks which we are solving, right? So one of the multi-class, right, is not always, this is again a binary class, right? This is again a binary segmentation task where your goal is to either classify each pixel into polyp category or non-polyp category or the background category. But there are also some multi-class classification tasks, right, in medical imaging domain which we are trying to solve. Like one is diabetic retinopathy multi-lesion segmentation task. Let me directly jump to that particular task, right? So, I mean, usually it is being detected through the retinal fundus images, and there are certain biomarkers through which it is being detected whether the person is having diabetic retinopathy, usually caused due to the diabetes disease. And there are certain biomarkers like microaneurysm, hemorrhages, hard exudate, soft exudate, and these lesions actually are very, very tiny, small, and distributed throughout this, distributed throughout this image. So it is very difficult to identify those actually areas, because sometimes one pixel or two pixels forms one particular region. Here you see the output of different or you can say the ground truth images of different biomarkers here, or you can say different biomarkers. Or here is the microaneurysm. The second one is hard exudate. The third one is soft exudate, and the fourth one is something no, hemorrhages. Yeah. Now this one is hemorrhage. This one is hard exudate and soft exudate, like this. Fine. So here is just an example I'm showing you. I mean, earlier actually this problem was solved, or this problem was considered as a binary segmentation task, where your goal is to either segment microaneurysm or hemorrhage. I mean, these are like independent segmentation tasks. For microaneurysm, you'll be having one model. For soft exudate, you will be having another model. So hemorrhage, you'll be having another model. For hard exudate, you'll be having another model. But everyone knows that, yes, if you can have a unified model that can segment all these regions, that will be really helpful. And this is how actually, if you combine the ground truth of all these classes, there are 4 classes, of course, and plus one background, plus one background. You see here, there are 5 classes in total. That means in the final layer, if you are planning to design a model, there will be 5 number of channels, right? So here again, every pixel has to be classified into 5 different categories, 1 background and 4 different classes. But if you look at the there's a huge class imbalance in here, right? I mean, you can see that there are some classes where you will find very small number of pixels, and there are some classes you will find most of the pixels are, let's say, red color. So red color here basically identify, let's say, excluded here, right? Hard excluded, which are looking yellow in color. So this hard excluded is having a lot of pixels, but if you look at the others like pink color for basically soft excluded, you will be finding very less number of pixels that forms this particular kind of thing. So you need to ultimately solve this kind of problem, which is really a challenging task. So we tried actually solving this problem. Actually, we've been trying to solve this problem. So here is again some of the results which we have obtained. So because this paper has been actually based in communication stage, so I cannot show you the model which you developed, but you can only see the results of our approach, the last one actually. So result of our approach, which is close to the ground truth. And if you look at the results of the other approaches, you will not find those, this kind of results. Even quantitative, even if you check the quantitative results also, so our model is really performing better than the other state-of-the-art approaches, including UNet, dense UNet, UNet++, Deep Lab, as I already discussed, Deep Lab, there's SegNet, CNET, and HACDR-net are like state-of-the-art approaches in this particular domain of research, right? So, okay, here is some of the output. Again, we have received multi-class segmentation task for this diabetic retinopathy multi-lesion segmentation. Very difficult actually compared to the previous problem, because here you need to identify all those lesions which are distributed across the image. So what are the challenges you will find actually while solving this kind of problems? Of course, if you're having less amount of data, so then you can think of, if you're having sufficient amount of data, at least decent amount of data, then you can think of adapting these foundation models with the help of this adapter. That's fine. But most of the time you will find the target domain which you are working on will not be having many data sets. Let's say you are planning to solve a new task for which data set is not available, and you could only able to get 100 images labeled from the doctors, let's say, especially, and there are thousands of images which you have collected is not having any levels. So then what you will do in that case? So you should actually go for semi-supervised kind of approaches in that case to deal with this data scarcity problem. So this is data scarcity problem. Here some of the images are labeled and some of the images are not labeled, right? And I mean, so in some of the cases, even you can think of, instead of annotating, if you ask the doctors to annotate or to provide this kind of ground truth, it is very difficult, right? Because it is a time-taking process, right? It's a time-consuming process, so even a cumbersome process also, right? So it takes around, I mean, a minimum half an hour to let's say for a single ophthalmologist to actually level at the pixel level, basically to annotate this image at the pixel level. So again, you cannot only trust on one particular ophthalmologist. You have to level, or basically you need to ask multiple ophthalmologists to annotate the same image, and then maybe some based on some majority rule and all, you can decide that whether the pixels should be considered as a you can say, let's say, hemorrhages or soft related like that. So then what is the other way? So what is the other way? Like semi-supervised is one of the ways, as I said, that some of the images are labeled and some of the images are not labeled. Another way could be weekly supervised. Like some of the, instead of giving like the whole pixel level annotation, if doctors can only give an area or bounding box under which that particular lesion is residing, so then what you can do is you can also think of yes, you can also think of designing some weekly supervised image segmentation techniques, which we are currently solving to actually arrive at something called as a better segmentation mask. I mean, but collection of data has become now easier, but annotation has become very difficult. So that's why it is just to avoid the annotation process. That's what is known as weakly supervised algorithms. And there are also certain other things which you can think about how to integrate uncertainty, or whether the kind of results which you have got is reliable or not, right? Because reliable in the sense, let's say in case of classification, reliability is easy to understand. Let's say the model has said that yes, this is the class level, but we need to also check it while generating the class level. We need to also check whether the model was confident in generating the class level or not, whether the model is confident or not. If the model is not confident, then the doctor has to be kept in the loop. So these are some of the challenges actually which you will encounter. And as I said, adapter is one of the solutions which can help you in avoiding that, fine tuning that whole larger models and all. Right. So I'll stop here, and if you are having any queries, here are some of the references from where I have taken some of the contents. If you are having any queries, I'll be happy to take one or two. Okay, let me now check the chart box. Is there anything? Okay, I'll say here, what is the approximation accuracy? Okay, as I said, actually, we're not actually computing accuracies over here, as I said, because there are a lot of background pixels I've shown you, right? So the IOUs, whatever we have got is around 85 and all. I mean, the dice loss, I mean, the dice score is also around that. But accuracy we are not computing actually. As I said, the limitations of these accuracies, because when most of the pixels are background pixels, you should not consider accuracy as a measure, right? So that is why it is always better to not use accuracy. I mean, in medical imaging domain, we are not using, because most of the pixels are background pixels. So otherwise, what will happen that you will get accuracy, let's say 70 or 80%. And in that case, also, if none of the pixels are none of the class and pixels are correctly classified, still you will get also 90% or let's say 85% accuracy, because all the background pixels are correctly classified, right? On all are, let's say, background pixels. So I'm not using that. Yeah. So any other queries? Can suggest model for skin lesion segmentation. See, yes. So I mean, from today onwards, you have seen, I think, right? Today you've seen the power of this SAM model, segment anything model. So in addition to the segment anything model, there are of course several foundation models like one former, mask former. These are all also known as foundation models. So now it is better to shift to the foundation model. Why I'm saying, because to get this type of the art performance. So if you want to design your model, you just focus on design your model. That is not a problem, right? So that is not a problem. But if you want, you can just simply use these foundation models. I mean, using adapter concept, you can design your own adapter. That also you can do. Otherwise, if you are really interested in designing your own model, then you can think of using the model, combining this, these layers, like, of course, this Mamba layers, and there are several variants of this Mamba transformer layers, convolutional layers, to get the better results. You know, to check, because actually skin lesion segmentation if you go through the literature, you will find, I think it's been 10 years people are trying to solve this problem. Of course, the data set size is increasing over the years. That's the data set. I think I still remember the data set name is ISIC, right? ISIC, I mean, there's some kind of data set actually. You will find out of 2016, 17, 18, 19, 20. So, I mean, you need to just check, first of all, what is the state of the art performance in this domain. And then what are the current state of the art approaches that has achieved those performance. And then accordingly, you have to decide whether you can beat those kind of results using only by proposing your own architecture and train it from the scratch with limited set of images. That also you can check. Okay, so then I'll stop here. Actually, if you're having any doubt, you can drop an email to me. I'm writing my email ID in the chat box. Okay, thank you.
Thank you, sir. Thank you, sir, for wonderful and engaging session. Your explanation made the topic easy to understand. We truly appreciate you taking the time to be with us and share your valuable knowledge. Once again, thank you very much, sir.
Thank you very much for the invitation. Thank you.
So, we will now break for lunch. The next session will begin at 2 p.m. Please kindly join back on time.